Welcome. Hi, my name's Scott Cooper. I've been working on fractured reservoirs for a couple of decades now, originally at university and then at the Department of Energy here in Albuquerque, New Mexico. And then John and I have started a consulting group here back in 2008 called Fracture Studies. And this is a continuation or a discussion of some of that work. And now I'll pass it over to John, who'll introduce himself and we're going to talk about.
Good afternoon, buenas tardes. I've got a PhD from Princeton University back in 1981 and I've been working on reservoir characterization for ever since then, doing some sedimentology, some fracture work. I worked for Sandia National Laboratories with Scott for a number of years. And together we have an atlas of natural and induced fractures in core that we have written. It will be coming out later this year, and we will be publishing it through Wiley & Sons. What we're going to be doing today is we're going to be talking about the difference between extension fractures and shear fractures as they affect permeability in a reservoir and deliverability in a reservoir. And it's an important distinction. You've got two basic kinds of fractures. Extension fractures are going to give you a whole different type of vertical permeability, horizontal permeability. They'll give you permeability anisotropy, the difference between shear and natural extension fractures as they affect the permeability. So we have to be able to recognize them. We have to be able to assign them the various orientations in the reservoir, and what we'd be doing is we'll be talking very specifically about the difference of extension fractures which have these plume structures, and this is a piece of core with a vertical core with the plume structures, and shear fractures. This is also a piece of core, and you see the surface of this fracture has a very different texture to it, a different morphology. And what do the extension fractures do? First off, they're poorly connected. So we've got poorly connected fractures in the lateral sense along one direction, but they are well connected, so they give you a very highly anisotropic drainage in the other direction. So the anisotropic drainage is highest parallel to the maximum compressive stress. And we have shear fractures. They're much better interconnected. They will give you radial drainage instead of this anisotropic drainage, and they are oriented oblique to the maximum compressive stress, which gives you a very different type of permeability and interaction with the stimulation fractures in the system. So now I'll turn it over to Scott, and away we go.
Hello, everyone. So one of the things we want to start at is to actually physically look at the fractures, and the physical examination of the surface will help us differentiate these different fracture types. We look at plume and arrest lines. They are very dominant on extension fractures, and the plumes are that plumose pattern here or feather-like pattern. And the arrest lines is this arcuate shape here of where the fracture was propagating from the right to the left and then slowed down in growth. Very distinctive for extension fractures. Another characteristic of extension fractures is they tend to form parallel sets, and they can be very parallel to each other. We see that in the FMI image log here on the right, and the summary of that data set on the left in the Rose diagram. These fractures are vertical and parallel in stripe. This has some very important production implications when we look at these. This is an outcrop photograph from here in the San Juan Basin. John was piloting the plane while I was leaning out the window and taking the pictures here. But we're looking at an outcrop with parallel extension fractures. Here in the desert southwest, the fractures tend to support more plant growth, so we can see the plants growing along the fracture trends here. Those are about at most 2 meters tall. And if we look at this, how is it going to influence drainage and interconnectivity here? You know, these fractures are parallel to each other with very little intersection, so there's very little interconnectivity. And if we start draining this particular reservoir out of one well, we see a very highly anisotropic drainage pattern. It will be parallel to the natural fractures. In some reservoirs, it's actually been documented up to 1,000 to 1 anisotropic ratio. So they have a significant influence on the reservoir here, these extension fractures. If we were to put in a second well, and it was a long trend with our fractures, we'd see a pretty quick interference pattern when we're doing primary production. If we were looking at doing an enhanced oil recovery and injecting a fluid in, we would also see a pretty quick reaction and a poor sweep of the matrix. But you know, if we've gone back and done our homework by looking at cores and similar, we can determine what the orientation of these fractures may be in our reservoir, so we can turn around and set up the better type of well pattern, wherein it's across the strike of these fractures. So when we do that, we get very little interference during primary production, and we get a better sweep. We're putting fluids in on the well here on the left. It's going to go out and go through the matrix and through the fractures until it gets to our producing well up in the upper right. So for a general conceptual model of extension fractures in a 3D cube here, we have parallel fractures. They tend to be vertical. They're also striking parallel to the maximum horizontal compressive stress when they formed. And when we look at the permeability of these fractures relative to the matrix, we'll see there's a high permeability, or highest permeability, parallel and along the fracture trend. It's greater than the matrix, whereas the permeability across these fractures is actually going to be equal to the matrix. So we get that better sweep if we're going across the fracture trend. Now, let's look at that other set of fractures, the shear fractures that John mentioned at the beginning of this. They have a distinctly different drainage and interconnectivity issues. These are conjugate shear fractures with a normal displacement shown in the photograph here. And they actually strike parallel to each other, but just like the extension fractures, we want to be able to physically look at the surface of the core or the outcrop. So we'll go to the next slide and look at this area here on the left. And we see these shear steps, not dissimilar from that core at the beginning of the course here, where we saw the steps on core. You see that similarly in the outcrop. All evidence that these are shear fractures. You could also have slicken lines in these shear fractures. Looking in the subsurface at FMI imagery, we see similar conjugate shear fractures. As I mentioned, they tend to be parallel in strike when there's normal displacement on these structures, and they have opposing dips. And we can see that in the FMI here. One dipping this way and the other across this direction. So they are intersecting fractures, but in a vertical sense. To get an idea of what I mean by this, let's look at an outcrop. There I am standing in southern Utah at this point, and we have these vertical conjugate fractures. They have normal displacement, but they are intersecting in this vertical profile, in this cross section. And if we are to think about how fluids may flow across these fractures, we have a permeability anisotropy. Again, it's going to be mainly parallel to the strike of these, but we are getting some interconnectivity across the fractures here. So we're getting a much better interconnected fracture network. In a block model, this is what that would look like. These normal displacement conjugate shears also strike parallel to the maximum horizontal compressive stress. The maximum permeability direction is parallel to the fracture trend, and it is greater than the matrix. But since we have that interconnected fracture system, we have better permeability normal or across that fracture trend, and it is greater than the matrix as well. We can have conjugate shears in different orientations. Another orientation that we see a lot in the subsurface and in outcrop are strike slip style conjugate shears. And this is an example of that type of outcrop. We're looking plan view down on a surface, and person with the nice safety boots on here is highlighting our fracture set. And so these are vertical and strike in different orientations. And a block diagram of what these strike slip conjugates look like is like this. The acute angle between these shears is actually parallel to the maximum horizontal compressive stress. This being the acute angle here, and that's parallel. Our matrix permeability is going to be, our fracture permeability is going to be highest, generally parallel to the main trend of our fractures, and it's going to be greater than the matrix. And note, yet again, we have a very intersecting set of fractures here, so we get good permeability normal to these main fracture trends. And again, that's going to be greater than the matrix. So in these unconventional reservoirs, when we have these nice intersecting conjugate shears, we're seeing a lot of good movement of fluids, both in the fractures and some better relationship of movement through the matrix as well. Next, let's look at a real-world example. This comes from here in the States. We're looking at two beds. They're separated by 100 feet of shale in this case. We actually logged horizontal core from both of these beds to document what type of fractures were in there. Let's look at bed A first. And we see in bed A there was about 152 feet of core that you wanted to physically pick up again, not just measure the strikes of these across the core, but look at the surfaces. And the surfaces shown plumes and the like, so we knew these were extension fractures. So we have bed A with a very parallel set of extension fractures. A summary of that data is shown here in the Rose diagram. with the primary set of fractures striking northeast-southwest in this case. And as we mentioned, that's got some pretty important fluid flow implications. Now let's look at what fractures were found in bed B. So in this case, we had about 136 feet of core, and the orientations of the fractures were showing two different trends. Physically pick up the core and look at the fracture faces, and you would see some of these shear steps on there indicating that these fractures were actually shear fractures. So log these, document them, and the summary data looks like this in a Rose diagram, where we have two basic striking trends of fractures. They're shear fractures, and so this bed is going to have a distinctly different permeability setup and fluid flow anisotropy in it. How can we kind of document that, and how do we look at that? Let's first look at these beds again. They're separate by 100 feet of shale. The upper bed has parallel natural extension fractures, and the lower bed, bed B, has this type of conjugate strike slip shear here. And we see a different interconnectivity of the fractures. But we can test these and see how the fluid flow is actually going through these fractures. We can do that by doing a tracer test, pumping it down an injection well on the left and pumping it back out a monitor well on the right and looking for this tracer. Now, going back to everything we've talked about up to this point, our conceptual model would suggest a couple of different reactions for these two beds if our wells are parallel to the strike of these fractures or the acute bisecting angle of the shears here, which they did in this case. So for bed A, I see a pretty direct line of fluid flow, the blue line indicating fluids flowing from our injection well on the left to our monitor well on the right. I would expect from the conceptual model that we'd get a quick breakthrough of the tracer and that it would flush through the fractures relatively quickly. From our conceptual model of bed B with these conjugate shears in there, there's a much more convoluted path for flow across the fractures, through fractures from one well to the monitoring well. It will take longer for the fluids to flow through this system, and it will take longer, I would expect, for them to sweep out through the fractures. So I would expect a later delivery of the tracer and that the tracer would last a little longer in this lower bed. So what were the results of that tracer test? And here we are. We have the tracer test showing a very early breakthrough with a quick drop-off of tracer, and then 20 days after injection of tracer, we start to get a second breakthrough. That breakthrough lasts almost 20 days before it's getting flushed out of the system. So just as we anticipated from the previous work by logging cores and determining the orientation of these fractures relative to our injector and our receiving well, we have a dual breakout with the first one being from bed A with those parallel extension fractures, and the slower breakthrough and slower return of all the tracer being here on the right through our conjugate shears in bed B. Now we can complicate these systems, and I'm going to show an outcrop here of extension fractures. In this case, we have two sets of extension fractures that are slightly oblique to each other. There's a set here nearly from the top of the photograph down to the bottom, fairly widely spaced, and a more closely spaced set of fractures going from left to right across the photograph. So if we have this type of intersecting extension fractures, what will affect or influence the horizontal permeability? What's going to control it in this case? And we need to start looking at some secondary effects in this case. How about the possibility that the most numerous set of fractures, the one from left to right across here, the most closely spaced one, is going to dominate the permeability. We'll get a little bit of draw-in from the more widely spaced fractures, but the closely spaced ones are still going to create an ellipse as we draw down this reservoir. Now, we can implications to this because we have this nice set of fractures that's been moving fluids. Over time, it's quite possible that this closely spaced set of fractures became mineralized. And if that's the case, if that closely spaced set of fractures is mineralized, fluids aren't flowing through there nearly as well as they may through that secondary, more widely spaced set of fractures if they're less mineralized. So then we have an anisotropic drainage that is parallel to this more widely spaced set of fractures. In other cases, we need to be thinking of what the stresses are like in the subsurface and how they may interact with our natural fracture system. So if our set of fractures is actually parallel to the maximum horizontal compressive stress, a couple of things are going to happen here. One is that these set of fractures parallel to that are going to tend to stay open, whereas the fracture set that is normal to our horizontal compressive stress or across it, it will get squeezed shut. And so the set that is aligned with sigma big H, or our maximum horizontal compressive stress, will dominate the permeability in this case. Now, I need to turn things over to John, and he will start the discussion about the additional differences between these fracture types, how stress sensitive these fractures are, and then how natural fractures may interact with hydraulic stimulation.
Thank you, Scott. Yes, this is, Scott has just reviewed the differences between the two fracture types in terms of the horizontal permeability, whether you've got fractures that are parallel to each other and give you high permeability anisotropy in one direction for the extension fractures versus the more isotropic permeability provided by shear fractures. So now we're going to look at some of the vertical permeability differences between the two fracture types. And the extension fractures tend to be strata-bound. These fractures here are confined to the beds. They terminate at the individual shale partings between the beds. So if you have a bedded reservoir and it has extension fractures in it, those fractures may not go vertically through the reservoir and may not give you good vertical connectivity within the heterogeneous reservoir. In contrast, shear fractures tend to cut across the smaller bedding plane. So here's a shear fracture coming down. It's cutting across this little shale parting in here, and the fractures give you much better vertical connectivity within a reservoir because they involve shear parallel to the fracture plane, which offsets some of these minor bedding discontinuities that are created by the sedimentology in the system. What about aperture? It turns out that aperture has also largely dependent on the type of fracturing in a reservoir. So here's some examples of cores with extension fractures in them. Now they're mineralized extension fractures, but you can see that the fractures have relatively uniform widths across and along their length. And the mineralization comes in and from either side, and you've got a reasonably uniform aperture down the center of the fracture. Over here you've had the fracture being mineralized, and then there's some secondary dissolution along it. But the fracture plane is reasonably uniformly wide. So extension fractures start out as reasonably uniform in terms of are going to be significantly different. Shear fractures, the apertures are going to be irregular, they're going to be offset, and they're going to involve a little bit of shear offset along them, which will give you larger apertures in some parts of the fracture and very narrow apertures where the asperities, the high point, have been pushed against each other. So the apertures of the fracture, of the two different types of fractures, are significantly different, and that reflects back on the permeability that they can afford. In addition, if you have a fracture face in a shear fracture, it is very commonly, if you've had significant shear offset, you may get a slickened side face on it. And this is a glassy face which will prevent the flow of fluid from the matrix across the fracture face and into the fracture aperture. So your slickened sides here, this glassy surface, affects the sigma parameter in a reservoir. How about the dynamics of a fracture? It turns out that most fractures, in fact, do not have a steady state permeability in a reservoir, but they have changes in the ability to change as the permeability as the changing stresses affect the fracture aperture. So if you look at the difference between an extension fracture, this fracture here, and they tend to be aligned with the maximum compressive stress, and a shear fracture will be oblique to the maximum compressive stress. And the importance there is that once you start changing the pore pressure within the fracture, you can create a system where you've got shear along this fracture and minor collapse along this fracture. If, however, you change this extension fracture to being normal to the maximum compressive stress, this fracture here can collapse entirely, and you will lose most of the permeability along that fracture just due to the reduction of pore fluids in the fracture itself. Here's an example. This is a laboratory example, and these were fractures that were from core, and plugs were taken from the fractures, and they were tested in the laboratory, and the conductivity of the fracture, which is this vertical scale here, has been normalized to 1. And the confining stress, which is the horizontal axis of the graph, has been increased from 1,000 to 8,000 psi, or about, I guess that's close to about 200 MPa. So what happens as you increase the confining stress down here, the permeability decreases in each one of these fractures, and that's because the aperture of the fracture closes. And these are extension fractures. These are fractures that you would not think would be terribly sensitive to stress, but they are. So the extension fractures are sensitive to changes in the stress. And here's an example from a real-life situation. This is a sandstone system where if you normalize the permeability in the reservoir to 1 and measure the changes up to 10 times more, or a tenth of the initial reservoir pressure, and you look at the pore pressure in the system, which changes, and as you change the pore pressure, of course, you change the confining pressure. The initial condition, the initial reservoir permeability was 1 at the initial pore pressure conditions. As you decreased the system, we lost permeabilities, 100 times permeability loss as you produced the well. The fractures were closing. As you increased, if you injected into the system, you got a system where you got enhanced permeability as you're opening up the fracture apertures. So that's what extension fractures are capable of doing in certain systems. How about shear fractures? Shear fractures are also stress sensitive, and let me illustrate that with another laboratory example. This is a standard laboratory system where you take a cylinder of rock, you put an artificial fracture in it, and then you inject laboratory oil down into the top of the system and measure the rate at which the oil escapes along this artificial fracture. And Bill Olson, who did this study, measured the fracture aperture, and if you think of this as an extension fracture, to do would be to change the normal stress in this direction across the system. But what Bill did then was he started to rotate the top half of the cylinder against the bottom half of the cylinder, creating out of this fracture a shear fracture. And what he saw was that the original permeability, this is permeability along this axis, this is the amount of rotation on the cylinder, the top cylinder against the bottom cylinder. The original permeability started to increase, and that's because the fracture is rough and the high points of the fracture started to ride up against the fractures, the high points of the fractures on the opposing face, and you actually increase the permeability. At about 2 millimeters, however, of rotation, the permeability started to decrease. So as he continued the rotation, the permeability decreased, and here he's lost about 25% of the permeability in that system. And he said, well, I wonder if I can reverse the permeability. And what he did was he took and he started to rotate it back in the other direction. And so from here on, he's rotating it again. He's measuring cumulative rotation. But he's rotating it backwards from here, and he has continued to lose permeability along the shear fracture. So the takeaway is that a little bit of shear is good. A lot of shear can reduce the permeability down to half of the original permeability. So shear fractures are a little bit tricky. You have to be careful how you look at them. All right, let's look at the differences between the two fracture types in terms of their interactions with hydraulic stimulation fractures. If you have a single set of extension fractures, you can have a vertical well drilled into that and put a stimulation fracture into it. And if the stress, the maximum horizontal compressive stress, is parallel to your fracture system, your hydraulic stimulation will come out and will follow not only the stress, but will also follow the mechanical weaknesses created by the natural fractures. If, however, your maximum compressive stress is normal to your fracture system, then you have a much more irregular fracture pattern. Every time you hit one of these mechanical weakness planes, the stimulation has the potential for branching and for being offset and for becoming much more irregular. It depends how strong the stress is. It depends how well cemented these fractures are. It depends on how well developed these fractures are as to how much of this you get. In addition, once you have this horizontal stimulation coming out here parallel to the maximum compressive stress, if you stop injection, what happens at each one of these little offsets? What happens is that you have the chance for closing them up, because this stress is going to act to cross that fracture plane. It's going to slam it shut, and you'll wind up leaving a lot of fluid out in the reservoir from your stimulation job. Suppose you have multiple sets of fractures. All right, this goes back to the photographs that Scott showed you. In order to understand how these will interact with the stimulation fracture, you need to know which set is mineralized, which set is aligned with the stresses, which set is the most numerous, and which set has the widest apertures. So this goes back to the argument that we really need to characterize our fractures in our reservoirs. We cannot just count them. We cannot just say our reservoir is fractured. We need to know what our fractures look like. How about shear fractures? Well, remember, the shear fractures are oriented at an oblique angle to the maximum compressive stress. The shear fractures, the stimulations in the shear fractures are going to get very irregular very quickly. You'll have high pumping pressures, you'll have high tortuosity, high potential for screen-outs, and the stimulation will not be as effective in a shear fracture system as it is in an extension fracture system. But it doesn't really matter, because the shear fractures are much better connected in most reservoirs anyway. So just to give you a quick summary of what we've been looking at, we've got extension fracture and we've got shear fracture. We've looked at the lateral connectivity. Extension fractures are highly asymmetric. Good connectivity in one direction, very poor connectivity in another direction. Shear fractures, we have pretty good lateral connectivity. How about the vertical connectivity? Poor in extension fractures because they tend to be arrested by the minor sedimentary heterogeneities in a reservoir. Shear fractures tend to cut across them. We'll get much better vertical connectivity. Apertures, typically an unmineralized extension fracture is a very good uniform aperture, what you'd like to have in your system. A shear fracture will be much more irregular. The fracture face permeability, it depends in part on the mineralization, but an unmineralized fracture face in an extension fracture is good permeability between the matrix and the slot of the fracture aperture. It's going to be highly irregular and variable for shear fractures. And the orientations relative to stress, if an extension fracture, you're going to be normal to the minimum compressive stress. You're going to be oblique to the stress system with a shear fracture, which all reflects on how these fracture systems are going to interact with the stimulation. So there's the conclusions. The fractures in the reservoirs are a reality. We cannot ignore the fact that there are different kinds of fractures, and the different types of fractures are going to affect how the reservoir permeability is going to behave as you start producing the reservoir. We can accurately characterize fractures if we're careful. We can look at the cores, look at the image logs. We can calibrate the image logs using pieces of cores, but we really need to know what it is we're characterizing. We need to know whether we're looking at extension fractures, shear fractures, faults. There's a number of different possibilities. We've only looked at 2 of them today. But we need to understand the fractures. That's the key point here. We need to understand them. We cannot just count them. We need to know how the existing fractures impart permeability anisotropy, how they influence the secondary reservoir recovery efforts, how stress sensitive they are. And many times we run up against the problem of trying to sell a coring program to management. This management looks at us and says, well, these are just science projects. No, these are not science projects. These are data acquisition products. These are the tasks, this is the work we need to do to accurately characterize a reservoir in order to the maximum productivity and the maximum recovery from it. if we don't characterize the fractures, we're not doing the science. So that's the conclusion of our presentation today.
Thank you.
Bien. Thank you, John. Let's pass to the question section. Por favor, sí, los que tengan alguna pregunta, alguna consulta sobre el tema que ha hablado John y Scott, por favor, hacerla por el micrófono, de hecho, en idioma inglés o en español, de ser el caso, y es así, se les podrá traducir la pregunta. Please, if you have any question, we ask you that you can do it by the means of the chat or by microphone in Spanish or English.
John?
Yes.
You can hear me?
I can.
Okay. Hi, I'm Tomás. I have a question about this how these fractures can relate in a reservoir that is being worked for geothermy.
For geothermal activities?
For geothermal activities. Because
Yeah.
in geothermal activities, you have a reservoir, you inject the fluid, and you have an output with the fluid.
Right.
So how can this study of fractures, or how can I study this fracture in the reservoir to optimize the output?
Okay. Do you have any cores? Do you have image logs? What does your data set consist of?
Right now I have like seismicity, imaging, and cores, but I do not have it right now.
Yeah, yeah. Well, for geothermal applications, you've got exactly the same types of problems you have for hydrocarbon reservoirs, in that the fractures provide the high permeability networks in the reservoir, and they give you the system that your fluid into and comes out of. So you have cores. We recommend that you take the cores and image logs and try to correlate the core fractures to the image log fractures, because that will make your image log fractures much more valuable.
Much more complete.
Mm-hmm. Is that address the problem?
Excuse me?
Does that addressing your question?
Yeah, kind of, but it's more like in the reservoir. I think I have the reservoir could be much better if they were like more pressure in the system.
Mm-hmm.
With more pressure in the system, I can retrieve more energy. So which one of these shear or extension fractures system could be the best for I to get the input?
Yeah, if you have a choice and you have what is given to you, regardless, but the better choice would be to have shear fractures, because they have a much better permeability network. But you know, that's just the geometry. You have to know not only the geometry, but you have to know the
lithology.
What your stress orientation is, what your stress anisotropy is, what your mineralization is like. In a geothermal reservoir, you're going to have to consider the possibility of mineralization of your fractures as you produce it, as you change the temperatures and the pressure of the system, because a geothermal reservoir is going to be a much larger temperature difference than in most hydrocarbon reservoirs. So you're going to have problems, potential problems with mineralization of your fractures during production.
Yeah, sulfur mineralization.
Mm-hmm.
Thank you, John. Appreciate it.
Yes.
Well, John, there's another question. I don't know if you are seeing it or you're actually watching in the chat, site,
Okay. About determining or distinguishing fracture systems from conventional logging tools. That is a difficult problem. There were many conventional logging tools run prior to the development of image logs that they ran specifically trying to understand fracture systems. They some of the resistivity logs were claimed that if you ran them twice, so if you ran them 2 times in your reservoir and looked at in the resistivity profile, you would be reading a deeper invasion the second time over a fractured interval. So that was one of the ones that they claimed would do it. There were suggestions that just the drill bit, when it was drilling through a fractured interval, would begin to chatter and would begin to get very difficult. You would get more torque on the drill string through a fractured interval. But none of these techniques that they have used using conventional logs have been 100% successful. As a matter of fact, if you were 50% successful with conventional logs, you were probably doing reasonably well. So it's a difficult problem, but there are various ways to address it. Yeah, sometimes you can begin to pick up, if you've got a pressured reservoir and you run through a fractured zone, the extra volume of the fluids from the fracture system will give you a kick system, just due to the fluid entry, the extra fluid entry along the fracture systems. But as I say, the more familiar you are with the specific basin where you're doing your drilling, the more confidence you can have in some of these conventional logs.
Right. Let's wait for another question. We already have time for that. Sí, por favor, si tienen alguna otra consulta, háganos saber para que John o Scott puedan contestarla. In geological mapping in surface, John, it happens that in any part of the terrestrial surface, since a plain coast or in highlands, you can find some outcrops with numerous or several faults. And faults, in fact, are shear zones. My question punctually is, every shear zone that I can see at the surface can have high probabilities in subsurface to generate a good reservoir?
The answer there is it depends. Faults originate as high permeability zones except where they don't, and that's a stupid answer. But the fact is that cut through multiple lithologies, and they have different characteristics depending on what lithology they cut through. They also are high permeability zones to begin with when they form, but because they are high permeability zones, they commonly get mineralized very quickly. So faults may or may not be high permeability zones in the subsurface.
And in your experience, faults, regional faults, can bear some, what kind of probability do they have to have in fact, a high chance to generate or stand for a reservoir?
Oh, they can be very high permeability. You can get a blowout well in some faults. You know, if the fault's cutting through a shale, the shale commonly will deform around the fault, and you can get pockets of fluid in the shale that are under essentially lithostatic pressures. And when you drill into the pocket of fluid, the fluid is at lithostatic pressure, but your mud weight is only, you know, half of that. And so you can get a blowout because of the high permeability along the fault. In other places, the fault is completely closed, completely mineralized, and you'll never even know that you're cutting through a fault until you log it and see an image log with a lot of fractures going along the fault. So it's a good question. It's a question that needs to be answered, but it needs to be answered on an individual basis. You can't say all faults are high permeability.
Yeah, you're right in the money. Yeah. There's another questions around here. ¿Hay alguna otra consulta, por favor? Pueden escribirla o pueden consultarla por el micrófono. You can write it in the chat box, or you can ask it to John directly.
Okay. So the question here is cores are good for estimating aperture. We fully agree. And orientation, strike. Do you recommend methodology for any kind of lateral extent? And again, that's a very good question, and you cannot really determine lateral extent from cores. What you have to do is to find an equivalent outcrop, and the outcrop hopefully would be a pavement outcrop, where you're looking at the bedding surface, and from that you can measure face lengths along the outcrop. And since the outcrop is in the surface, you have had different stresses on it than what you see in the subsurface. But the outcrop will give you an idea, a concept of how susceptible that formation is to fracturing. If it is fractured in the outcrop, it is likely to be more fractured, at least, than other formations in the subsurface. So the outcrop gives you a range of lateral extent, a range of fracture lengths. And that's about the only way to develop an idea of the lateral extent, because core data is one-dimensional data, as you note, and it will not give you any information on the two lateral dimensions. Even if you go horizontally with a core, you're not going to get the lateral extent of a fracture unless that fracture is parallel to the core, and that's very unlikely. So there really is no methodology that I'm aware of, that we're aware of, for determining fracture length from wellbore data.
Wayne Narr had a methodology for spacing,
Yeah.
which had several conditions on it, particular fracture types.
Thank you, Sandra. Yeah. I think there can be some last question. Yeah. Una última pregunta, por favor. ¿No? Si tienen por ahí alguna más. ¿Sí? There's it is. Says, how do these fracture types behave across various lithofacies, and how that is affect fracture connectivity as explained? If you overlay faces, would you think some of the permeability conclusions would change? That's the question.
So if we're looking at fracture heights and how they would propagate through numerous beds, extension fractures tend to be the ones that terminate more likely at little bed boundaries, little alike. The shears tend to have a little bit more stress bump, I guess. You know, they're being propagated a little bit more directly, so they will cut several beds at a time. So they'll have more vertical connectivity in the reservoir as well, which again makes them desirable.
Yeah. And there's another question from Side. No? Side tell us, could shear fractures inhibit fract hits?
Yes, as Scott showed, the fracture type very strongly dictates the orientation of your interference between wells. So if you have fractures that are parallel, all your extension fractures are going to form in parallel sets, and if you have only one set, then you'll have much better communication with wells that are oriented along the strike of the extension fractures than between wells that are across the strike of the extension fractures, as a couple of those graphs that Scott showed. Now, if you have shear fractures, which are much better interconnection, then you're going to have a difference in the interference between the different wells. So the communication between wells in shear fracture sets is not nearly as directionally controlled. You're more likely to get interference between wells in different orientations with shear fracture sets.
Well, it's done. Yeah. So, John and Scott, it's been a wonderful meeting with you. It was a pleasure to have you, all of you here. So there's not any other thing to say. Thank you a lot, and we hope to have you in other chance, in other moment. You know. Yeah. Yeah.
It was interesting and fun.
It was fun. We enjoyed it. Thank you very much.
Yeah, we're very pleased with this. Y esta charla podrá visualizarse en nuestro canal de YouTube el día lunes. This meeting and broadcasting will be published out in our YouTube channel at this Monday at night. Thank you, all of you. See you then.